We're going to continue looking at the internals of the parallel streams framework, focusing now on the partitioning phase. And that's the phase, of course, that's responsible for taking the original data source and partitioning it or splitting it up into different chunks. The way that's done, of course, as we've talked about before, from the point of view of sequential streams, is by using a splitterator, which is a splittable iterator. And we talked about before how that's used for a couple of different purposes. So earlier, when we talked about splitterators for sequential streams, I showed you how you can use a splitterator in order to traverse the elements in a source. So here we have an example where we've got a famous Shakespeare quote, and we can then get a splitterator to that list of strings that forms the quote, and then we can use the try advance method to print each element out one at a time in counter order from left to right, which will say, "This above all, to thine own self be true." Now that we're looking at parallel streams, we can go a little deeper and we can talk about how parallel splitterators can be used to partition all elements in a source. And that's done, of course, by the other method in the splitterator interface, which is the try-split method. So we've got try-advance, which is used for traversing, and then we've got try-split, which is used for partitioning. And it's the streams framework that calls try-split. An application, user code, and so on doesn't call try-split. It's done by the framework in order to be able to partition the original data source up into smaller chunks. So let's take a look at how try-split works. So the basic idea of try-split is to try to take a big data collection, data source, and then chop it up, literally chop it up like I show with my animation here, into smaller chunks. And ideally, if you have the right kind of collection, it'll be able to split it evenly and it'll be able to split it efficiently. And the way the splitterator works is when you're splitting, when you're in the splitting part, you're going to go ahead and split the input up into two chunks, and the right-hand side of the chunks will be this object. So you'll update the state in this object to correspond to the right-hand side of the split. And then you'll return a new splitterator that'll cover the left-hand side. So that's the way to think about it. One new splitterator is created that goes for the left-hand side, and there's an update to the state of the right-hand side splitterator. This is a good example of why modern Java is a so-called hybrid language. So here's a case where we're actually modifying state of an object as opposed to making two new objects, which would be the way you do it if you're doing a purely functional approach. So Java 8 is a compromise intended to be able to be as efficient as you can while still giving you lots of cool functional properties. Okay, if we use a splitterator, you'll notice that the way this happens under the hood is always done in a single thread of control. So splitterators don't need to have any internal synchronization. They don't need to have a join phase. That's all handled for you automatically by the framework, by the streams framework. So that greatly simplifies the work that you have to do to write your code, and it also eliminates a whole slew of inherent and accidental complexities because you don't have to worry about synchronization in your code. The framework handles that for you. Try-split will be called recursively by the streams framework until all the chunks are less than or equal to some minimum size. Now, for something like an array list or your unsynchronized array that you wrote, that minimum size was defined to be 1. So we split down till we had an element that was atomic, literally. Not every splitterator needs to work that way. There's other splitterators, such as the ones we'll talk about in the context of the search stream gang case study, where you don't want to split down to the size of 1. You just want to split things up to the point where you're getting a boost from parallelism. If you split things too fine-grained in some circumstances, you spend too much time splitting and not enough time running in parallel. And so there's kind of a trade-off. Most of the Java collections, however, split down to an atomic size of 1. But if you don't like that for some reason, if you discover through benchmarking that that's overkill, then you could always change the implementation of the splitterator to split down to size k, where k is greater than 1, if you so chose. Might be overkill, but if you can always benchmark your code, you can always find out what the right split size would be. When the chunk size of a given splitterator object is less than or equal to the min size, at that point, try-split is finished, and then it goes ahead and returns null. And when null is returned from try-split, that is basically an indicator to the underlying streams framework that the chunk should be processed sequentially. And so if you have a size of 1, then it's pretty easy how to do that. And if you take a look, for example, at your splitterator that you have for the array splitterator for your unsynchronized array implementation for the assignments you've been doing, you'll see that that try advance thing really just consumes one element. But in general, you could consume multiple elements if that's the way in which the size worked. And we'll see some examples of that later. Here's a couple examples of Java collections to compare and contrast how splitterators work in practice. We'll see sometimes Java splitterators work very nicely to split evenly and efficiently. So the Arraylist Splitterator is a good example of that. The Arraylist Splitterator is very similar to your unsynchronized array splitterator. And as you can see here, we have try split and try advance. And what they're going to do is try split will split the array evenly until there's nothing left to split. Kind of see what it does there. And then try advance will consume a single element when it's called in order to be able to get that element out of the right part of the list and give it back to the streams framework for further processing as a stream. However, there's other Java collections that don't split evenly and don't split efficiently. And probably the best example of this, because it's a nice foil or a nice comparison point with Arraylist, is the so-called linked list splitterator. So the splitterator for linked list is not as efficient, and one reason why it's not efficient is it doesn't split evenly very well, because of course to split evenly in a linked list you have to go traversing through the list one pointer at a time until you find the midpoint. And at that point you could split it evenly, but it would take a long time to find the midpoint, especially if there's a big list, because you don't have random access. A linked list is not a random access collection, whereas an array list is a random access collection. You can go find the midpoint by just doing a computation. Now, of course, you have to be careful what that computation does. You have to compute it correctly, but once you compute it correctly, then it makes life easier. So what linked list splitterator does is it actually splits by something called a batch unit, and it adjusts that over time to do clever things. And if you look at the code, you can see it's very complicated, and there's lots of looping and copying and all this other stuff. So it probably comes as no surprise that this is not as efficient as the Arraylist splitterator. The try advance implementation is also a little bit more complicated. It's not super duper inefficient. It's just more complicated than the one we have for Arraylist. And that's because you have to do some pointer following and so on in order to set it up for the next operation. Okay, so those are just kind of comparing and contrasting a couple of built-in Java splitterator implementations to give you a good intuitive sense that some of them are more efficient than others. We're going to cover the implementation details for parallel splitterators shortly when we start talking about the search with parallel splitterator version of our Search Stream Gang case study. But for now, just be aware that they're more complicated to write sometimes than doing things that are purely sequential. So that's an overview of the partitioning phase. I think some of this stuff will be even more intuitive once we look through a concrete example of implementing sophisticated and complex parallel splitterator, which we will do here in the not too distant future.